S dot AM, Sij, this I group, okay, these two terms over here, you see, these two terms over here, as this one, okay, I just sum, okay, K here will be 1 and 2 on this case. Now, this here is Lij N dot AM. Attention, N is related to this A3 over here, which is perpendicular to A1 and A2. It's quite clear, you see? And AM belongs to the vector space, okay? And N, the normal vector, belongs to the dual, okay? That's the dual, okay? A3 over here. So this will be 0. Now, the gamma ijk, I define as Sijk. I just substitute over here, okay, quite clear. So this is capital S. Attention now, this is capital S, okay? The vector is equal gamma ijk ak. So the vector. K varies in this case from 1 and 2. So then now this term here, okay, the vector V dia, in this case over here, let's write, let's write here, this is Vi. You see, I just copy from here and I wrote over there. Then I substitute this Vi, Vj, gamma ijk, ak. So it's equation 3. Now, substituting 3 into 1 yields. Now dv of dt, dv of dk, tt. Attention now, look at here, now easy. VIAI, I could set VAAK, because I here is a dummy, okay? That's what I wrote over here. So I group this term here, and this I put AK. So this is a covariant derivative, okay, of vector V with respect to the scalar t. When the t is time, this is acceleration, okay? In general, you can call lambda, okay? Different from time. So this in general is a covariant derivative. Sometimes dv of dt is substituted by nabla, okay? The covariant derivative. And also we derive several properties of the covariant derivative, you see? So I will use in the next video, okay? That's it.